Welcome to Web Handling. This is the second in a series on DFM, or Design for Manufacturability, with a web handling emphasis. In this segment, we will talk about common material properties that are known to cause trouble, at least on occasion. Before we begin, it would be useful to define a material property and how it differs from a physical property, as both are measured in test labs. A material property is something you can measure on a test specimen that is relatively independent of physical size. Commonly tested properties include strength and modulus, and they depend mostly on chemistry and processing. On the other hand, a physical property does depend on size. Examples include thickness and weight. There is an area of overlap and confusion that is epidemic in plant test labs. That is, what are the units for the value or the numbers given by the test instruments? Some units are peculiar to a specific test and will not be discussed here. However, many are a blend of material and physical properties. Let us give the common example of strength. The most common units reported would be pounds force in the U.S. system and perhaps grams or newtons in the metric system. Presumed by standard is the specimen width and the thickness of the sample being tested. Yet the proper engineering units for material strength are PSI in the U.S. system and pascals in the metric system. These could be obtained if you knew width and thickness and whether the tensile tester was already dividing by width before reporting. Very few people in test lab know what units are actually being tested and reported. Sometimes you get really mixed units for strength, such as grams, a mass unit, and not even force, per 1 inch wide sample. Material property measurements can come from a variety of instruments. However, they are most often found in the test lab and almost always codified by company or organizational standards. In web handling, as we will find, the tensile tester is where you can get more than a few of our properties of interest. We will only focus here on a few properties that are well known to be troubles for web handling. We will start with an obvious one, strength. As strength is reduced, the risk of web damage or even breaks increases. TEA, or ductility, is a related property. TEA is the area under the stress-strain curve rather than the peak as strength is. Low TEA is a risk for web breaks if the machine mechanical and control precisions are not very high. Modulus, sometimes called flexibility or stiffness by the layman, can be troubles at either extreme. It is difficult to hold width tolerances and eliminate some types of wrinkling when materials are very flexible. On the other hand, stiff materials such as paper and foil demand much more for machine precisions to avoid a host of problems, certainly too many to be mentioned here. Finally, if you bond two materials together that have differing moduli, you can expect curl. This is an epidemic product process design problem. Yet, the severity of curl can often be predicted before you even make the product. We have simple one-line equations and even a free internet app to do the calculation for you. The coefficient of web-web friction, abbreviated COF, can be troubles at both extremes, and this trouble will mostly be on the winder. In fact, some manufacturing lines must alter the COF solely to make the product windable. High expansion rates due to water add-on or heat risk one type of MD wrinkle, sometimes to the point of not being able to make the product. The expansion can be measured or calculated. The range of threshold of pain is between 0.1 and 1% for a wide variety of products and processes. In other words, pain is again predictable long before you even make the product. Finally, a low Poisson ratio, such as is common with nonwovens, make tight width tolerances next to impossible. Physical properties can also be challenging, and we would be remiss not to mention at least two of the most important ones. Thin webs are challenges for a variety of problems, including web breaks, wrinkles, and tension control. Thick webs are not entirely easy either. Path control can be very difficult, as stiff webs want to go where they want to go, unless you know how to redirect it through the science of guiding. However, the number one trouble of thickness is not thickness per se. It is the variability of thickness. Decades of experience tells us that the thickness variability of 1 to 10% can give us a range of troubles that varies from unnoticeable to unsaleable. Obviously, measuring and controlling variability is more challenging on thin materials, but even the thickest may not entirely escape bagginess and many other winding troubles that might result. Finally, width might matter more than you might think. Controlling machine precisions in the path of ribbon-like materials is in some ways more challenging. However, wide webs will really test system reliability. A single defect lane in a 1 meter wide web may render that entire meter unsaleable. A single defect lane on a 10 meter wide web might also, depending on the defect, make the whole web unsaleable. Also, the risk of wrinkling rises noticeably once one gets near and certainly beyond 1 meter wide. These and many other challenges make scaling up from pilot to commercial widths worse than merely proportional increases in trouble. Again, units are important. Here again you can see some truly strange mixes. For example, the standard basis weight measure in nonwovens and textiles in the U.S. is OZY. That stands for ounces per square yard. And paper weight is measured in pounds per ream. And that ream might be 1,000 or 3,000 or perhaps some other number of square feet, depending on which paper grade you're talking about. The metric equivalent is much more sensible in many ways and is usually simply GSM or grams per square meter. Even here, we have mixed units because it should be kilograms per square meter or grams per square centimeter. Confusion like this allows a degree engineer to work but more slowly. However, it makes even the simplest math untrustworthy by almost everyone else. Thank you so very much for watching this module in my Plant Practical video series. Stay tuned for the next clip where we will take a much deeper dive into the extra challenge of thin materials.